The first area we're really interested in today is the inverse of a matrix. So once we have a linear transformation, if that linear transformation is both injective and surjective, so if it's a bijective linear transformation, that means that every input to that function has one and only one output because it is a function, but also every output that we could possibly associate with that function also has a unique input. That's the surjective and injective pieces of it. And so for a bijective linear transformation, there is a one-to-one correspondence. Every different input in the domain has a different output in the codomain, and every possible output in the codomain is associated with some one and only one input back in the domain. So if we go to our cat picture that I keep coming back to over and over again, here's an example of a linear transformation. Let's say it's this one, where any point that I pick in the domain is going to have a unique point in the codomain. Well, that's obvious because we have a function. But also, any point that I choose in the codomain is going to come from a unique point back in the domain. And that is what makes this a one-to-one and onto, in other words, an injective and surjective, in other words, a bijective linear transformation. So this is an example of a bijective linear transformation. Every point over here corresponds with exactly one point over here, and vice versa. So in that situation, we will be able to come up with a linear transformation that exactly undoes whatever the original linear transformation does. And the benefit of that is that if I want to solve an equation involving that linear transformation, I can just apply the inverse transformation to both sides of my equation and have my x, my variable, whatever it is, solved for immediately. So that's the real joy of having an invertible linear transformation, is we can use that inverse to then solve the equation that we're trying to solve. And so to the first phase of today is going to be about trying to decode how can we tell when a linear transformation has an inverse, and then once we know that it has an inverse, how do we find a matrix that represents that inverse? So we're going to look at it in two different ways. The first one, we're going to look at it through the lens of the standard matrix of a linear transformation. That's going to be kind of what the first section is about. How do I find a standard matrix for the inverse of an invertible linear transformation? And then from there, just by taking a closer look at the work that we did to find that standard matrix, we'll come up with a different procedure for finding an inverse for a matrix, where we don't have to, well, it's about the same amount of work. We just have to think a little bit less, which is always a little bit dangerous, which is why we learn the richer way first, and then the way that involves a little bit less intentional thought second. So that's the plan for the first part of today, after which we'll get a chance to talk about row operations and what row operations have to say about the geometric properties of our linear transformations. So there's the agenda.